On May 24, 2013, a magnitude 8.3 earthquake ruptured beneath the Sea of Okhotsk in Russia's Far East. The seismic waves carried enough energy to rival the most destructive tremors in recorded history. But the rupture did not happen near the surface. It began deep inside the Earth's mantle, plummeting roughly 600 kilometers underground. Near the surface, the mechanics of an earthquake are straightforward. Large, brittle blocks of tectonic crust grind against each other. Friction locks them in place, elastic strain builds up over decades or centuries, and eventually the rock snaps. Take that exact same mechanical process 600 kilometers downward, and physics dictates it should be impossible. At that depth, the ambient pressure from the surrounding rock is immense, squeezing rock from every direction tightly enough to instantly close any open crack. The temperatures are entirely hostile to brittle failure. Mantle minerals are hot enough that they slowly creep and deform like heavy plastic over millions of years, rather than snapping cleanly in seconds. Yet the dense, jagged black ink on this seismograph records a violent, rapid release of energy from these extreme depths, proving that catastrophic ruptures happen in an environment completely unsuited for them. This diagram illustrates a cross-section of tectonic boundaries. On the right side, a specific pattern emerges. These deep focus earthquakes are strictly confined inside enormous, dense slabs of oceanic lithosphere, sinking from subduction zones, where one plate is forced beneath another. Rock is an exceptionally poor conductor of heat. As the slab descends deep into the earth, it acts as a massive thermal time capsule. It preserves a cold interior and remains physically distinct from the hot rock around it, carrying its surface temperature, old internal faults, and accumulated stress hundreds of kilometers down. Deep focus earthquakes represent a piece of the surface world actively failing inside an alien environment. To see how that failure happens, we have to look at this schematic of olivine, a magnesium and iron silicate that makes up much of the upper mantle. At the surface, its atoms hold a relatively open, loose structure. As the slab sinks and pressure rises, that pressure forces those atoms to rearrange themselves into significantly denser, tighter crystal forms, eventually breaking down into entirely new minerals. But the center of the sinking slab is unnaturally cold. That low temperature kinetically blocks the atoms from moving fast enough to build the new crystal structure. The olivine is pushed far beyond the pressure where it should have transformed, trapped in an unstable delay known as a metastable wedge. If this delayed mineral simply collapsed into its denser form all at once, the rock would shrink inward, radiating a tiny implosion. Seismographs, however, record aggressive lateral shearing motion during deep earthquakes. The transformation has to generate active sideways slip, not just a reduction in volume. Laboratory experiments have replicated these extreme conditions to watch the transformation in real time. Instead of a smooth wave of structural change sweeping through the rock, the delayed olivine collapses into microscopic pockets called anticracks. These are tiny, lens-shaped zones filled with exceptionally fine, nanometer-scale grains of the new high-pressure mineral mixed with the old olivine. A material's physical strength depends heavily on the size of its internal grains. These extraordinarily fine nanocrystals are highly deformable. As extreme pressure persists, more of these microscopic lenses form. They grow, intersect, and connect, turning a wide, distributed volume of stress into one continuous, razor-thin weak layer. Deformation that should have taken millions of geological years concentrates entirely within this microscopic band, providing a path for a seismic event lasting only seconds. Ambient pressure and a delayed phase change cannot start a rupture on their own. High-pressure laboratory tests reveal that the rock requires intense physical shearing to actively trigger the transformation. This flowchart tracks the resulting feedback loop. Tectonic stress forces the plate to bend, causing initial plastic deformation. That physical strain fractures the trapped olivine crystals and actively forces the high-pressure mineral phase to form. The newly transformed material is incredibly fine and mechanically weak. Since the surrounding rock is still dense and strong, further deformation is forced to concentrate inside this exact spot, causing the narrow fault to slip and generate friction. That friction drives the final phase, thermal runaway. The faster the material deforms, the more intense heat it generates. That extreme heat severely lowers the rock's resistance, weakening the band even further, which permits even faster deformation. The mineral phase transformation initiates the local instability, and runaway shear heating propels the resulting rupture outward. The Sea of Okhotsk earthquake tore through 180 kilometers of solid rock. A single microscopic phase change inside a tiny lens of olivine cannot explain a rupture of that magnitude. This cross-section shows how the large-scale geometry of the descending plate scales the instability up. Around 660 kilometers deep, the sinking slab hits the denser, highly viscous lower mantle. The plate does not slide through cleanly. It folds, buckles, and tears, producing the massive local strain variations necessary to feed continuous stress into the newly weakened shear zones. Scientists continue to refine the exact balance of these triggers. Earthquakes at shallower intermediate depths are often promoted by water, escaping from hydrous minerals and lubricating faults. Warm slabs that cannot easily preserve a metastable wedge also host deep earthquakes, pointing to variations in how thermal runaway initiates. The geographic distribution of these tremors provides strong evidence for the mineral transformation model. Deep earthquake activity peaks near 600 kilometers and then falls rapidly, with nearly all events stopping entirely by 700 kilometers down, the exact depth where the olivine mineral transformation is finally complete. The 2013 rupture beneath the Sea of Okhotsk was the violent conclusion of a process that started millions of years prior. A cold, stressed fragment of a tectonic plate collapsed beneath the weight of its own stored structural memory, shearing apart as its minerals violently rearranged. These immense earthquakes occurred deep within the Earth because a cold piece of the surface world had not yet had the time to finish becoming the mantle around it.